if we have 2 points in the xy plane and the horizontal distance between these points is delta x and the vertical distance is delta y, and I don't mean horizontal distance and vertical distance, I mean horizontal displacement from first point to the second, vertical displacement between the first point and the second. In any case, if these displacements are delta x and delta y, then the distance between the points is, by the Pythagorean theorem, square root of delta x quantity squared plus delta y quantity squared. And that distance is the length of this line segment. Between the points. Now, if the slope between these, well, if the x and y displacements are delta y and delta x, then the slope of our segment is delta y over delta x, and we could call that, if we wish, m for slope, m being a common letter applied to the slope of a line segment. Now, if delta y over delta x is m, then delta y can be expressed as m delta x, and the distance between the points is square root of delta x squared plus m delta x squared, delta y being m delta x, which simplifies to the square root of 1 plus m squared multiplied by delta x. Simply factor a delta x squared out of what we get if we expand this, and so forth. And this should be familiar to you from previous courses and from the study of arc length in your first semester calculus course. Now, if this segment approximates a section or part of a curve corresponding to a function y equals f of x, then the slope at this point, if we regard this point as being a point, let's say x naught, y naught on the graph, or let's say a point x naught, f of x naught on the graph, then this function, if it's continuous and differentiable, will have a derivative which at this point might well be equal to the slope of this line segment, or it might have an average derivative over the interval equal to the slope of this line segment. In that case, we could let m be represented by the derivative f prime. And for this model then, the distance between points is approximately I started to get ahead of myself. I wrote down an F here where I shouldn't have. Let's go back a second. we're looking for the expression for the distance between the points. I need a statement to precede this. The slope is m, which is approximately equal to f prime of x naught. So the distance between the points is approximately the square root of 1 plus f prime of x naught times delta x, and it's f prime of x naught quantity squared multiplied by delta x. I've made a correction here. Simply, the expression I had before was correct, but not written very well, not very clear. So this is a clear picture of the expression. Anyhow, the point now is that the length of an arc of the graph of this function, starting at some arbitrary point x naught f of x naught and moving for a small distance delta x, is going to be equal to this expression. Again, something you should be familiar with from first year calculus. We're going to extend this idea to the idea of an arc, well, not an arc length, I'm sorry, the idea of a surface area for a function of two variables. To begin to make that connection, make sure we're on the page here. Again, we have our displacement. We have a delta x and a delta y that is now equal to, let's say, f prime of x delta x. Not using the x naught notation at this point, so we consider this to be any point on a graph of a function, and we ask ourselves, okay, if this is the delta y and delta x, then how is that related to a vector perpendicular to this surface? That is, it's what we're going to call a normal vector. And this is going to be our connection between arc length on a function of one variable and surface area on a function of two variables. Still with the two-dimensional case, what's a vector in the direction of n? Well, if we let this segment coincide with a vector, that vector would be delta x I plus delta y j. Of course, delta y is f prime of x delta x. This vector being perpendicular to this one is any vector whose dot product with this is 0, and a convenient choice would be n equals negative delta y I plus delta x j. In terms of our function f of x and its derivative, of course, delta y is f prime of x delta x, so that this normal vector could be written as negative f prime of x I plus j multiplied by delta x. That is, delta y is f prime of x delta x. So if we write delta y that way, we'll have a delta x in both terms, which we can factor out, leaving us negative f prime of x I plus j. The ratio of the arc distance to our delta x down here along the x-axis is square root of 1 plus f prime of x squared. If we resketch our segment, with delta y and delta x here, and our normal vector, our n vector here. We can sketch the projection of the n vector on the y direction. So here's delta x, here's delta y, here's our n vector, and here's our projection of the n vector. I'm not going to specify the direction. I'm simply going to observe that this angle and this angle are the same, so that we have similar triangles here. The projection of n being simply this side, and the arc distance being this side, so the projection being this side of this triangle, the arc distance being this side of this triangle. We can set up a proportionality and conclude that the arc distance over delta x equals the magnitude of n over its projection. So that the arc distance equals magnitude of n over the projection of n times delta x. I'm not being real specific about what projection we're using, because when we go to 3 dimensions, the axis on which we're projecting is going to change, but the picture is going to remain pretty much the same. And the thing you should understand before we do that is simply that if we know the vector n perpendicular to this segment, then by simple calculations on n, just by magnitude of n and projection of n on a certain axis, we get a number we can multiply by our delta x to get the arc distance. In a very analogous way, we're going to be able to take a vector normal to a graph in 3 dimensions, a graph of a function of 2 dimensions, f of x, y, find the normal vector at a point, project that normal vector onto an axis, and that's going to be simply the projection onto the k-axis, and get a number we can multiply by our area increment to get our surface area. And I'm going to make a statement by way of close analogy with this. So close analogy. The magnitude of n divided by the projection onto our k vector of our normal vector multiplied by an area increment in the xy plane, or in an r theta plane if we prefer, is equal to the surface area lying above, and I guess we'll come over a little bit, surface area lying above our area increment. Now we want to become more specific about this, so we'll do that starting in the next clip.